Today on How It's Made. Industrial casters. Wedding cakes. Terahertz spectrometers. And racing catamarans. Industrial casters are used to move heavy equipment from one location to another. The wheels make it easy to move mining machinery, large medical devices, or factory carts, wherever and whenever it's required. The size of the object determines the size of the casters used to move it. Heavy items need casters with thicker wheels. Some larger objects may need multiple wheels to evenly distribute its weight. First, they make the top plate, which mounts the caster underneath the object. They begin with a thick sheet of steel. A computer-guided cutting machine combines oxygen and electricity to produce plasma. This incredibly hot flame melts the steel to cut out the part. They make several other caster parts out of steel coil. It's a thinner, more flexible type of steel. They feed it through a punch press. The press strikes it with a yoke-shaped die. The yokes are the arms that hold each side of the wheel axle. Workers place each yoke piece in a forming press. The press bends the piece into the required shape. It also makes a circular groove around the hole in the middle. Next, they fill the groove with steel ball bearings. These bearings allow the yoke to swivel. This steel retainer holds the ball bearings in place. They fill the grooves of a steel cap with ball bearings as well. Then they place it in a punch press and position the yoke on top of it. The press joins the cap to the yoke's retainer, sandwiching the ball bearings in between. After riveting the top plate to the yoke, they put a steel seal over the retainer. They lock it in place with a pneumatic press. This factory purchases nylon wheel inserts from a supplier. Workers place the inserts in an injection molding press. The press melts neoprene rubber and injects it into the mold. Once it cools to a solid state, the machine ejects what are now rubber-edged wheels. This process takes about 4 minutes. The rubber edge absorbs shock, reduces noise, and prevents damage to the floor. When this factory needs to make larger wheels, they use a different injection molding press, one that can make wheels 5 times larger than their standard models. It works exactly like the other injection molder, except it only makes one wheel at a time. A worker carefully places the wheel on a cool-down rack for 2.5 hours. The wheel molds are made of 2 parts. The parts form a seam once attached. A worker grinds down the rubber seam until the surface is smooth. Now that all the caster's parts are ready, assembly can begin. First, they place a 2-part bearing inside the wheel and lock it in position with the pneumatic press. Next, they install a steel guard on each side. The guards prevent anything from getting inside the wheel and inhibiting its movement. They position the wheel between the yokes and insert the steel wheel axle. A bolt head secures one end, and they attach a nut to the other. Then they tighten everything with an impact gun. They inject grease to lubricate the ball bearings. This factory runs random samples through a series of quality control tests. A machine applies weight and counts how many revolutions the caster can withstand before it finally breaks. This factory also makes special casters for oven and freezer carts using rubber wheels, built to withstand extreme heat or cold. Their ball bearings are also lubricated with grease that doesn't freeze or melt. Casters can also come equipped with a foot-activated brake. Wedding cakes have become bigger and more elaborate over the years. Today's wedding cakes are multi-tiered and even multi-flavored. They're typically covered in fondant icing and decorated with ornate sugar flowers. The finished product is an edible work of art, perfect for that special day. These customized wedding cakes are covered in fondant. This special icing acts as a canvas on which delicious designs can be created. The baker starts by making chocolate cakes for the bottom tier. Once the cakes come out of the oven, she transfers them directly to the fridge. The cool, firm cakes are easy to slice into layers. She spreads buttercream frosting between the layers. The frosting ingredients include lightly salted butter, icing sugar, and Dutch cocoa powder. Layer by layer, she builds the tier to the desired height. She puts the tier back in the fridge. While it's solidifying, she makes the gum paste that will be used to craft the edible flowers. First, she adds icing sugar to egg whites. Then thins out the mixture with a teaspoon of water. Next, she adds food coloring. She mixes the ingredients for a couple of minutes until they're thoroughly blended. She adds Tylose powder, a synthetic version of gum arabic, to harden the mixture. After another 15 seconds of mixing, the gum paste is ready for kneading. The baker rubs some vegetable shortening on her hands for lubrication. She sprinkles some icing sugar on the table to prevent the gum paste from sticking. Then she kneads the gum paste for 5 to 10 minutes. Now the artistry begins. She uses a set of modeling tools made of food-safe non-stick plastic. First, she makes a little hat out of the pink gum paste. Then she rolls out another piece until it's paper thin. The baker uses a gum paste cutter to cut out several teardrop shapes. One at a time, she lays the teardrops out on a hard foam mat. She thins and curls the edges with a ball-tipped modeling tool to create a natural-looking rose petal. Then she switches to a scribe tool. She curls back the edges to make the petal even more lifelike. Then she applies tasteless edible glue. She adheres the first petal onto the point of the gum paste hat. She wraps it all the way around to create the center of the rose. The baker attaches the next layer, this time using 2 petals. She adds several additional layers using 2 more petals each time until the rose is complete. She snips off the base of the hat, then lets the glue dry for 15 minutes. The baker uses green gum paste to make the leaves. She rolls the paste thicker at the base and thinner at the top. Then she presses the sheet against the top of the board to produce vertical veins. She centers her leaf-shaped cutter over one of the veins and cuts out a leaf. After attaching a wire to the base, she uses a silicone stamp to imprint smaller veins on the leaf. This makes it look more realistic. The baker curls the leaf's edges with a round tool. She uses a different tool to deepen some of the veining and complete the leaf. The baker sets her decorations aside and removes the cake tiers from the refrigerator. She firmly applies the fondant over the chilled chocolate frosting. She made the fondant earlier with melted marshmallows, butter, icing sugar, vanilla extract, and food coloring. She applies fondant to the remaining tiers, then stacks them. She begins decorating this cake with ribbon and Italian lace. She attaches the flowers with stiff edible glue made from egg whites, icing sugar, and lemon juice. She can also make edible ribbons and lace by pouring liquid gum paste into the appropriate molds. This special gum paste uses corn syrup and cornstarch to reach the right consistency. A magnificent custom-made cake is designed to be a showpiece at the wedding reception. Admired, devoured, and always remembered. Terahertz spectrometers use invisible light to see through objects, including living tissue. These T-rays are an emerging technology that allows objects to be imaged and analyzed. It's a form of radiation that is non-ionizing and believed to be non-destructive. An alternative to X-rays and ultrasound, terahertz technology generates a light that can't be seen by the naked eye, but it can see what lies beneath the surface. The technology has potential applications in the medical, security, and manufacturing fields. Production starts with the circuit board holder for the transmitter sensor head. Computerized tools drill a hole into a cylindrical piece of brass and carve bridge slots to hold the circuit board. Another tool transforms a second brass cylinder into the main body for the sensor head. This is the completed sensor head body. A technician screws an optical collimator into the housing. This device separates the laser light into parallel beams. He inserts a lens in the housing. The next piece he installs adjusts the position of the circuit board holder in the spectrometer. He selects a circuit board. It has a sensor chip in the center that emits terahertz light. He places it into the holder and slides the holder on the sensor body. He uses steel pins to lock it in place. The worker fastens a larger lens on the end. A device holds the sensor head in place as he tweaks the position of the circuit board. It must be perfectly aligned in order to receive the laser beam. He attaches a round circuit board to the sensor head. This board will allow the sensor head to establish electrical connections. Next, he installs the collimating module. This device has a larger lens than the sensor head, so it can send parallel terahertz beams further. He attaches a retainer ring to the module. The technician screws the collimating module to the sensor head. Now the spectrometer transmitter is complete. He slides the base of the stand into a rail system. He installs a receiver at the other end of the rail and connects fiber optic cables to both the transmitter and the receiver. The next technician assembles the optical chassis that scans objects for imaging. He installs lenses in specific locations within the aluminum chassis. He attaches a mirror to a rail in front of the lenses. The moving mirror will bounce laser light to scan images. He tests the rail system to make sure it shuttles the mirror across the spectrometer chassis. The technician places the chassis on a steel panel and wires the fiber optics throughout. He connects the fiber optic cable to the laser generating unit. He screws an acrylic glass cover to the chassis. Then he secures the chassis and laser unit to the cabinet panel. Technicians mount the panel to the back of the spectrometer cabinet using brackets and screws. Once it's solidly in place, they install the cabinet door. The door allows for easy access during servicing. They lock the door, then screw on the top lid. The spectrometer is ready for the transmitter and receiver assembly. The technician pushes the fiber optic cable through a hole in the lid and makes all the connections. He tests the device using a plastic bottle. The transmitter sends terahertz light through the bottle to measure its thickness and analyze its chemical composition. The receiver collects the data for computer analysis. This terahertz spectrometer is now ready to scan objects and show them in a new light. Thousands of years ago, the Polynesians built the first catamarans. Then in 1876, an American redesigned one for racing. It was so fast that it was deemed unfair competition and banned from organized racing. But eventually, racing catamarans made a comeback in the late 20th century. With 2 hulls instead of 1, catamarans skim the water faster than traditional sailboats. While a single-hull boat relies on a heavy keel, a catamaran uses its width as leverage to harness the power of the wind. A racing catamaran starts with foam material for the hull's lightweight core. A worker clamps the foam to a fiberglass form. Then he places it into an oven and closes the door. The oven gradually brings the core temperature up to 160 degrees Fahrenheit. After a few minutes, he takes the foam out of the oven and places an upper form over it. The softened and malleable foam bends to the form's contours. After applying a gel coat and fiberglass fabric in a hull mold, he lays in the shaped foam pieces. He fills any gaps in the core with slivers of foam material. He adds little squares of porous plastic to reinforce areas where hardware will be attached later. The worker drapes fiberglass fabric loosely over the core. He sprays a small amount of rubber cement onto the core and presses the fabric into it. The cement helps the fabric stick to the core. Then he stretches nylon fabric over the fiberglass and foam. He runs spiral-cut tubing along the sides of the mold. He cuts it to the right length and tapes it down. After laying down a plastic mesh, 2 workers cover the mold and its contents in plastic. They secure the edges of the mold with tacky tape, creating a tight seal. The team connects a vacuum to the spiral tubing on one side of the mold. When they turn it on, the vacuum sucks out the air, pulling the layers tightly together. They prepare a vinyl-based resin and apply it using the vacuum tube. The vacuum pumps the resin through the layers of fiberglass and foam. The resin takes a couple of hours to dry. The team removes the plastic, mesh, and nylon layers, revealing 1/2 of a catamaran hull. Next, they install the bulkheads. They use special tools to accurately position them in the hull. They also place bulkheads in the second half of the hull. The workers join the 2 hulls while they're still in the molds and seal the seam with epoxy. They remove the hull from the molds and cut an opening for the trunk. It holds a retractable centerboard for curbing sideways movement. They attach the screws used to lace the trampoline platform. A worker applies glue-back strips of plastic to protect the fiberglass from chafing. He screws sailing hardware to both hulls. The hulls are placed in an alignment jig. Then, the team installs crossbars that fit into molded recesses. They attach a rudder system to each hull and test them to verify they operate correctly. The trampoline platform is made of polypropylene. The front slides into a molded groove. They lace up the back and sides with double-braided synthetic rope. He pulls the laces tight to keep the platform rigid. Once the other sailing control lines are in place, they're ready to hoist the sail on this racing catamaran. From start to finish, it takes 3 weeks to produce a racing catamaran. In competition, these boats have been clocked at 3 times the speed of wind.